All right, so you should see my screen here, and we got through the first several slides sort of introducing the idea and why it is that we need to talk about induced stresses, understand that it's one type of total stress. And thinking back to our idea of effective stress, we have to include all sources of total stress and also the water pressure, right? And so once again, in Module 5, we focused on geostatic total stress. So only that one type of total stress, but now we're considering what happens when other things come into play, like structures, or even, which can cause a positive increase in total stress, or even excavations, which can cause a negative influence, like a decrease in total stress. So we've gone through some of these. We have to consider all of the different sources of total stress when we're considering the effective stress at a point, right? The effective stress at any one point. What are all the total stresses at that point, where one of them is the geostatic total stress, but then other stresses like induced stress, right? All of them at that one point in order to figure out the effective stress, right? So in this way, we often think about it in terms of the change in stress. So you'll see me write it many times like delta sigma, again, because the geostatic stress was there before construction and it's there after construction. The difference is, well, what did the construction do? What is the stress that's induced by our actions, induced by the construction, right? So the change in stress from the initial to the final, before construction to after construction. What was the change in stress that's expected? And that's sort of what we're looking at here. And again, the fact that it's a localized load is what makes it a little bit more complicated. You have to consider the boundary conditions. You can't just sort of consider it to be a total, you know, an increase in stress as if it was like another layer of soil and just include it into the geostatic. You can't really do that if it's relatively small and localized. So that begs the question then, what is relatively small? Okay, how do we define relatively small? Right? So we looked at a couple reasons why we might have to consider induced stress. We started getting into our idea of the terminology here. So we have this X, Y, and F in terms of the stress element. And once again, we have our horizontal stresses, sigma X and sigma Y. We have several different shear stresses that would act on this soil element. Again, this is the point of interest, the one single point where we're trying to determine the stress, right, and the change in stress. There's also the shear stresses here, and we're ignoring all that. For right now, we're only focusing on the vertical total stress, so sigma sub z. And what is the change in that, or what is the vertical total stress that's induced by this point load in this diagram, or by some other kind of localized load? So we talked about elastic theory. We went a little further into this. We're only focusing on the vertical total stress that is induced. I started introducing the concept of, or the concept that was created by Boussinesq and then developed slightly differently by Westergaard. Okay, so it's often called the Boussinesq theory or the Boussinesq equation. All right, and so I think this is just about, these next couple slides is just about where I left off. We have to understand the idea of the boundary conditions. Now, when the load is very, very sort of wide and spread out over a wide area, and your point of interest is nowhere near the boundary conditions, right? Nowhere near the boundaries, then essentially everything is really just vertical. The change in stress is really only vertical, or the induced total stress is really vertical, and it becomes relatively simple. Like it says on this slide here, the stress induced at some depth may be 100% of the stress applied at the surface. So let me clean up this slide a little bit and reuse it. Okay, so let's understand what I was talking about there. The stress induced at some depth may be 100% of the stress applied at the surface. That's what we call Q. So the original ground surface at the top of this sand layer, and then we now have this new fill causing this new stress on the original ground surface. We'll call that Q. That is not the stress at A, but it causes some influence. It causes some change at point A. So if Q is applied up here at the surface, then the question is, what is the change in vertical total stress? Or in other words, what is the vertical total stress that is induced by Q? Okay, and once again, if the load is very, very wide, and you're talking about a point of interest that is not influenced by the boundary conditions, so far away from the boundaries of the load, then perhaps delta sigma z equals Q. And what would be, and actually let me put this in better terms for what we're heading towards, 100% of Q. In other words, point A experiences all of the new stress that was applied some distance above. That is possible in some situations, especially when the load is very, very wide. Okay, and what is Q? Well, actually, let me say, in this case, Q would be, well, what is the unit weight of this fill, and what is the height of the fill? So in that sense, it's really just like a new layer of soil, adding to the geostatic stress, if it's very, very wide compared to point A. And again, that begs the question, what do I mean by compared to point A? Well, we have to consider the depth of point A from, again, not the original ground surface, the depth from where Q is applied. In this particular example, they're the same. Q was applied on the original ground surface, but it's not always that way. Okay, so what is the depth of point A? And again, what is the distance away from any of these boundary effects? Okay, so if the load is very wide relative to point A, then perhaps the induced stress is really just equal to 100% of the applied stress that is above it. Okay, so surface load that is very, very wide, it's reasonable to assume that the surface load influences the soil at depth, even outside its own footprint. So not only point A, but to some different degree. What about maybe point B, even outside of its own footprint? And in the previous class when we were talking about this, everybody agreed that there would be some influence, even outside of the footprint of the load. How much? Well, that's what we're going to head towards. We're trying to figure that out. But we all agreed that there's some influence, right? Like point D, which is outside the footprint of the load, is not directly below the load itself, but there is some influence. And then I went further. Okay, so we have to consider what is the influence on the load, the applied load Q on these different points, okay, to try and figure out what is the induced stress at these different points, okay? Then I went on and I said, I developed this idea of an negative influence. So when we remove soil, or we create some kind of negative stress, what used to be, and again, remember, the key here is you have to consider where the load is applied. You have to consider where the load is applied. On that plane, again, so this is maybe some like in plan view, some rectangular excavation. But on that plane that I just colored in black, on that plane, there used to be some load caused by the weight of the soil above it, the weight of the soil in the excavation. When that excavation soil was removed, on that plane experienced a negative Q. A negative Q. It used to be higher than what it is right now. Does that negative Q applied on this plane right here have some influence below it? We all agreed the other day that, yes, we all felt like the stress at point B would go down. Originally, it was some geostatic total stress, but because of the excavation, the stress has been reduced. The total vertical stress at point B has been reduced because of a negative influence. But even, once again, outside of its own footprint. So even, I think we all agreed, even at point A, there would be some negative influence caused by this excavation. That the stress at point A will be less than it used to be before the excavation. Okay, that's where I left off previously, but on the next slide we see that we have to consider these, we have to consider what's possible overlapping zones of influence. Okay, so consider a surface load distributed over a relatively small area. That's sort of what we're talking about here. The load is not felt by the soil outside of a somewhat pyramidal, like a pyramid-shaped zone of influence. And that's exactly what we've got here. In 3D, you know, we're just seeing it in cross-section. In 3D, this sort of zone of influence, everything inside of this zone might have some influence. And in 3D, this goes into the page. This would be like sort of almost a pyramid-shaped zone of influence that's below this load. Okay? But like it says here, the load is not felt by the soil outside of that pyramid. Okay, now the approximate method in your textbook, one of your homework problems, actually I think two of them maybe, asks you to use the approximate method. And the approximate method considers this pyramid shape. It considers this as like a 2-to-1 slope for the sides of this like sort of pyramid shape. It's not really exactly straight lines. It's not really exactly 2-to-1 slope, but it's something similar to that. In fact, this influence zone is approximately 45 degrees, going outwards from the edges of the load, right? 45 degrees approximately. Now again, that approximate method is not exactly what I'm doing here. It considers a 2-to-1 slope. And it, using simple geometry, then derives some equations, all right? So what exactly are we getting at? Well, I want to look a little bit deeper at this idea and talk about these influence zones, overlapping influence zones. Okay, so actually, you know what? Let me just take away all of these things. All right. So let's say we have our original ground surface right here. And, well, there's a couple ways to look at this. What if I put a structure and maybe point A right here is the point of interest. And we're considering the induced vertical stress at point A. And I put a structure that looks like this. And just to keep it simple for now, let's say that I put the structure just on the original ground surface. Okay? So this is what we've been talking about already. We understand there is some influence from this structure on point A. What about if there's another structure right next door? And so close together that there's not even really any space between them. So, structure number 1 has some influence even outside of its own footprint. Structure number 2 also has some influence even outside of its own footprint. And we can see right here now, point A is actually being influenced by both of these structures, each of which is creating this sort of bearing pressure, Q1 from structure 1, and maybe a little bit different, Q2 from structure 2. Both of them are influencing point A, and we have to simply consider the influence of both. Maybe we have the induced stress from structure 1 and the induced stress from structure 2. They are both influencing point A. Okay? Now, what if I then tear down structure number 2? What if I tear down structure number 2 and remove it? What happens to the stress at point A?
You got some negative stress influence coming from where structure 2 used to be, so it's gonna be able to move in that direction.
That's right. So a negative influence coming from the fact that that structure is no longer there. The stress at point A was at a certain level, and then when I demolished building 2, the stress went down. There's a negative influence at point A from the fact that structure 2 is now missing. And yet the stress at point A is greater than it was before any of the construction. It's greater than before structure number 1 was put there, but it's less than, when structure number 2 was removed. So again, we have these overlapping zones of influence. And in that sense, the way that we can start to recognize boundary conditions is that the fact that there's a load in sort of area number 1, where structure number 1 is, the fact that there's a load for structure number 1 has a positive influence on point A. But the fact that there is no load next to it, that's like a negative influence on point A. Okay? Let me clarify that a little bit further with another diagram. Okay. This is sort of oversimplified, but it gets the idea of these influence zones. So we have a structure similar to what I was just talking about. And we're considering point A. Let's say right here. Okay. Point A is influenced by this structure. So it's within this influence zone. We often assume it's basically 45 degrees. What that means is outside Okay, I'm back. Got this down to like less than a minute. I don't really know what the problem is. I think it's my Wi-Fi. Just can't keep up or something like that. But let's get back to it. Okay, so as I was saying, this is really about boundary conditions, which have to be considered when it's a localized load, relatively small. Okay, a relatively small localized load. I'm working towards the idea, well, how small is relatively small? Okay, so the fact that there is no load applied next to this structure, structure number one, has a negative influence on point A. Sort of like that. But what if we were to consider maybe point A prime? We can see there now that point A prime, just directly above point A, some distance, point A prime is not influenced in that negative influence zone. It's outside of that sort of essentially 45-degree influence zone. So point A is influenced by the positive structure, but also the boundary conditions, that negative influence, that because there's nothing outside of it. But A prime is influenced in the positive zone, but not by the negative zone. So notice A and A prime, I purposely put a little off center for the load. But what if we move over a little bit? Like point B and B prime. So in this way, because of the boundary conditions and sort of these overlapping influence zones, I'm just looking at one structure, but sort of this negative influence because near the boundaries, there's a negative influence, the fact that there's no load out there. But again, we can have one structure next to another one, next to another, and all of them have overlapping influence zones, sometimes positive and negative, all right? And so what we see here right now, A prime and B prime are the same depth, but they are different horizontal, or in other words, lateral distance away from the center line. A and B are both at the same depth, but they're a different lateral distance away from the center line of the load, which is right here, okay? And then A and A prime are different depths. B and B prime are the same lateral distance, but they're different depths. And so in other words, the distance from the center line to the edge of the load, right? If I say that this is, well, it's a rectangle in plan view. Let me say that this is the width of the load. I'll call that B. In plan view, maybe it looks like this. B is the width, L is the length of this rectangular structural footing, okay? So the distance away from the center line to the edge is B over 2, right? And so the maximum distance from the center line to the edge is B over 2. And so what we see now is that the distribution of induced stresses depends on two things. Both the depth from where the load is applied, I'll call that ZF, and also, going back to our earlier diagram, that sort of XF or YF. which was that lateral distance away from the center line of the load. Okay, that lateral distance away from the center line of the load. I'll call that XF. Okay, so point A prime probably has the greatest induced stress because it has all positive influence and no negative. Point B prime is probably a little less than that. Same depth, but it's getting close, or it's on that boundary of the negative influence. And then point A is less than that, is closer to the center line, and then point B, same depth as A, but a little further away from the center line. Okay, and so we could start to envision that maybe the induced stress at A prime is greater than at B prime, which is greater than at A, sorry, not the effective stress, the induced total stress, greater than at A, which is greater than at B. So this is just intuitively, if you think about these influence zones, you might be able to agree with my statement right there. Okay, but we're working towards more details. Okay, so again, the approximate method considers it to be something very similar to this. It assumes a 2-to-1 zone, and if this is the actual bearing pressure, the foundation of the structure, right, and then we go to some depth below that, that's this Z, some depth below that, we have to take this pyramid shape and essentially extend it downwards. So B is the width and L is the length of the actual bearing load, bearing pressure. And then we have this B plus ZF because it's a 2-to-1 slope, L plus ZF. So assuming that, we can do some basic geometry and say, well, pressure over area. Since the area is increasing with depth, then the force and the stress is decreasing. Okay, the total weight of the structure divided by a larger area as it increases with depth in sort of this pyramid shape. That's the basic idea of the approximate method. The equations are developed for that, right? And I do ask you to do that a couple of times just so you recognize it. It's very commonly done in construction, not so much in engineering, where we really try to be a lot more accurate. Conservative practice often assumes a 1-to-1 slope instead of a 2-to-1. Okay, which simply makes it more safe. And again, that's where that 45 degrees comes from. If you go away from a structure, you know, outside of that 45-degree influence zone, then you really don't have to worry about affecting that structure or influencing the soil that you're working on. Okay, so that's the approximate method. But we say that the induced stress decreases with depth because the load is distributed over an increasing area as you go sort of downwards in that pyramid. But consider an excavation in a continuous soil mass. So actually, I already sort of talked about that. The fact that some soil is missing decreases. So now, let me sort of unhide this slide. All right, so now let's talk about an excavation that precedes a structure. So we have our original ground surface, and that is needed only to calculate the original geostatic effective stress. Let's say point A right there. The original geostatic effective stress. But we have to consider that the stress on this plane at the bottom of the excavation, the stress at the bottom of the excavation is now less than it used to be. And that is going to influence point A. So delta sigma from excavation, okay, delta sigma from excavation has to be considered. All right. Now, Q excavation is simply going to equal what is the unit weight of the soil that was removed times the depth of the excavation. That is the stress reduction that happened right? That's the stress that reduction that happened. I don't know, maybe I'll call this point B. The stress reduction that occurred at point B is equal to the weight of soil that was removed. And that's right here. But the question is, how does that influence point A? Okay, then we come and we build a structure. And the bottom of the excavation, point B, is now the bottom of the footing. It is the bottom of the excavation, and it's also the bottom of the footing. So Q structure equals, often we call this the bearing pressure or the footing pressure. Okay, the footing load or the bearing pressure caused by the structure. Okay, what we have to consider for point A is that, actually, for the influence of point A, but for the load applied, this is from my structure. Okay, we have to consider Q net. The net pressure applied at point B, the net pressure, point B was right here, the net pressure at point B is, well, there's a positive pressure applied by the structure, and there's a negative pressure from the excavation. We need to consider both of those. And that is the net pressure applied at point B, which then gives us what is the induced stress at point A. All right, so we have in the exact same location, both of them applied at point B, not the original ground surface. Okay, both of these pressures are applied at point B. We have first the excavation, which is like a negative bearing pressure because soil was removed. Point B experiences this Q excavation. And then as the structure is built, and it takes some time, a few months or maybe even a year or two, as the structure is built, then we have the bearing pressure that comes from the structure. Point B experiences the net difference. By the end of construction, point B experiences that net difference. The question really is, what about point A? What does point A experience? Well, it experiences that net difference, that Q net, but as it influences the soil below it. And because it's a localized load that is going to be influenced by boundary effects, it's probably not 100. It's probably not equal to Q. It's not 100% of Q. There's some stress reduction as you go down with depth and as you move over lateral distance away from the center line. Okay, so now we also included this idea of not only influence zones, positive and negative, but also this Q net idea when we have an excavation and a structure both in the same location. Okay, so now we can move forward. Back to that fill. So since no load is applied outside the boundary of the fill, you might expect a reduced stress. So we talked about these negative influence zones already. I've covered that. Let's see what this really looks like. Okay, here's my induced stress at depth below the point load. So if the point load was applied right here, this is what I see on the right is not physical distance, it's not lateral distance from the point load, it's a plot of stress. So how much stress is there directly below the point load? What would be the stress right there? Well, that's this much, okay? 100% of the point load is felt if you're talking about right below the point load. But as you go down with depth, the stress is dissipated, okay? And so what if we have layered soil? Oh, actually, let's consider no layering. If E1 equals E2, and E is the stiffness modulus, the modulus of elasticity, essentially the Young's modulus for the soil. If both soils are the same stiffness, then they both react exactly the same way, and it's really just like one uniform layer of soil. It's not really two layers if they're both the same stiffness. And so we see that here in the middle. Okay, and so what we see is as you go down with depth, the stress reduces relatively rapidly. And then at some point, it sort of asymptotes. If you kept going deeper and deeper and deeper, eventually there'd be a point at a certain depth below the point load that doesn't even feel the point load. It is not influenced by the point load at all. At a certain depth, it doesn't even know that there was some load P that was applied. Now, what if E1, what if the top layer is stiffer than the bottom layer? That's right here. If the top layer is stiffer and stronger than the bottom layer, then pressures are dissipated even more rapidly. But that asymptote comes a little quicker and eventually asymptotes to zero. It's like the upper layer being stronger and stiffer is sort of protecting the lower layer. Okay, so pressures dissipate even more rapidly. However, if the if the upper layer is softer than the lower layer, then pressures extend down deeper and they don't dissipate quite as rapidly with depth. So these have been measured. We've done experiments with this, put small holes in the ground, put load cells and try to measure stress and measure force, and we can actually measure this. So this actually comes from real data. And we've tried to develop our theories based on this. But although this is for a point load at the surface, which is not something we commonly do with soils. Okay, this comes from elastic theory, right? And so Boussinesq took this and he developed our theory for considering, first of all, just a point load. If we put a point load somewhere on a soil mass, and then we go some depth down, what is the depth to point A, and then the lateral distance away from the center line to point A. What is the depth and lateral distance from the point where the point load is applied to the point of interest? So really this diagram is to give terminology. Of course, we can understand if we want to line up our axes that r squared equals x squared plus y squared. Okay, P is the point load, Z is the depth, not from the ground surface, which we may not even be seeing here, but Z is the depth from where the load is applied to the point of interest. Okay. From point of application, not from the ground surface, but from where the load is applied to the point of interest. R, then, big R, is this 3D sort of radial distance from the point load, of course, x squared plus y squared plus z squared, and little r. So this is our sort of symbols and terminology that we're going to use. Boussinesq then went on and developed the theory. His theory ended up with this. Where I is the influence factor. I is the influence factor. Okay, so we take the magnitude of the point load and the depth z squared. So first thing we see is that if we go back up, that it's not a linear relationship. I was sort of showing these linear influence zones. Well, that was not about actually stress distribution. That was just about boundary conditions and influence zones. If we look at the actual stress distribution, we see that this is a non-linear dissipation of stress with depth. Okay, and so we actually see now it's z squared. So the pressure dissipates rapidly with depth, dissipates with the square of depth. But then what's a little bit more complicated is this influence factor, which includes not only a z squared, but also an r squared. So it dissipates rapidly with depth, and it also dissipates with lateral distance away from the center line of the load. Okay. Now we could work on shear strength as well as shear stress as well as normal stress, but we're not really going to worry about that right now. We're worried once again only about the induced total vertical stress. So it always looks like this, IP over Z squared, but this influence factor I has a few different terms in it, including R and Z. Okay, so dissipates rapidly with depth and not quite as rapidly with lateral distance away from center line. Again, I is this influence factor. So the only thing that really matters, or the only thing that really changes for different kinds of loads, is this influence factor, and I'll come to that in just a minute. So this is point loads, and Boussinesq first developed this theory, developing exactly what is I and how is it related to P and Z squared. Okay, and so very simple example. If we had a point load, like let's say it is at the ground surface, and we go 10 feet down and 7 feet over, what is the stress caused by this 2,000-pound point load? 2,000 pounds is not large. Of course, we also don't often have point loads. But let's say it's some relatively small and sort of heavy object, 2,000 pounds. That's not very big for stress. But we can see, we simply plug in R and Z. We get our influence factor, bring that back up here. 3.5 pounds per square foot. Now that's not the stress at point A, that was the stress change caused by the point load. The stress that was induced just by the point load. What was there before the point load was geostatic, but now it's geostatic plus induced. Okay, so 3.5 pounds per square foot doesn't sound like a lot, but that is something. Of course, 2,000 pounds is also not very heavy. Okay. So let's move forward, because point loads are not really what I'm interested in. They're actually really quite rare in geotech. Because soil does not have a really high bearing capacity or bearing strength, you have to take a load and spread it out over an area. A bigger area means less stress. And so almost always in geotech, this is the first principle of foundation engineering, right? And so in geotech, we are usually concerned with distributed loads, not point loads. So how do we do distributed loads? You can see this in Caduto, and basically the idea is you take Boussinesq's point load theory and integrate it over an area. Now we can talk about circular loads, and we integrate it from the center of curvature, integrate it outwards around the circle. We integrate it for a line load, a 1D line load. A strip load is really very, a line load might look like this, essentially a 1D load, whereas a strip load is really pretty thin in one dimension, but very long in the other dimension. It's also called a semi-infinite load. So it's small and finite in one direction, but very, very long in the other direction. So that's what we call a strip load. We also have strip footings that are usually 3 or 4 feet wide, but could be really, really long, hundreds of feet long. Okay, so that's a strip load, or often called a semi-infinite load. Right? We could talk about circular loads, square loads, rectangular loads. And don't forget, a square is a rectangle. It's a special kind of rectangle, but a square is still a rectangle, right? Uniformly varying loads, like a wedge embankment, something like in 3D that looks like this, right? We could have loads that are linearly increasing. Okay, so like a wedge load. So different people have done these integrations. Okay, so let's take a look at each of these. When talking about distributed loads, it always looks like this. Always. For a distributed load. For a point load, it was that IP over Z squared. But for a distributed load, Q is the bearing pressure. Okay, that is applied. Q is the applied load, I sub sigma, they're just talking about stress influence. I don't usually put the sigma on it, but I is the influence factor. So every kind of distributed load always looks like this. The only difference is, for different shapes, there's a different influence. So a circle versus a strip load versus a square, a rectangular load, different influence. And so we have to focus on the influence factor. Other than that, the induced stress caused by a distributed load always looks like this. Okay? Delta sigma, vertical total stress, is always equal to the influence factor times the applied load Q. Okay, so let's take a look. This is in your book. If we look first at a circular load. So we have a circular load, whether it's at the surface or not, doesn't matter. We may have to consider an excavation and this idea of a Q net, right? Whether this load is applied on the ground surface doesn't matter. And don't forget, ZF is always the distance from the point of application, the distance from the load, not the distance from the ground surface. So I want to say this right now because you guys are going to ask me, and I'm going to refer back to this comment right now. Okay, please remember this and maybe write it down. It is always, always, always the depth below the point of application. Okay, or in fact, it's for a distributed load, a plane of application. The distance below, the depth below where the load is applied. Okay? But along with that, it is never, never, never the depth from the ground surface. Write it down, trust me. Write it down. You're going to get confused, you're going to ask me. So put this on a sticky note and put it right there on your monitor or something. Okay. So we have this load that's distributed into a circular area, and it is applied at some point in the soil, and we have a depth below the load, ZF, and a lateral distance XF, the lateral distance away from the center line. Okay? B is the diameter of the circular load. B is the diameter of the circular load. So this circular load is applied at some point like this. And we have this ratio of X over B and Z over B. So what this is telling me is something we saw earlier. That how wide is a wide load? Depends on how deep are you talking. Let me go back just for a second. How wide is a wide load? Depends on how deep are you talking about. Right? Actually, it was this one here. For point A prime, that is a very wide load. There is no negative influence. It's not affected by the boundary conditions. But for point A, it's not really a wide load. It is affected by the boundary conditions. There is some negative influence at point A. So how wide is a wide load? Depends on what is the depth that you're talking about. Okay, so you have to relate the width of the load, we're calling this B, to the depth. And that's where this X over B and Z over B comes from. It's related to, X over B and Z over B, because the lateral distance and the vertical depth both are related to the width of the load. So when the vertical distance from center line equals 1/2 of the diameter, that means you're talking about a point that's right on the edge of the circle. And we can see we can see a stress concentration right there, right? When X over B equals 1/2, when distance from center line equals half the diameter, that means you're at a radius. You're right on the edge of the circle. So directly below the center is where we see the maximum stress. But when we get to the edge, we still see some stress. It's not exactly zero. Then as we go down with depth, we still see that at any depth, directly below the center is the maximum stress. As you go a lateral distance away from the center line, you still have some stress. Okay, so how do you use a chart like this? You have to interpolate between the lines, just like reading between grid lines. Okay, what we're looking for is the influence factor. All right, so if I know the diameter of my circular load B, if I know the depth to the point of interest, and the lateral distance to the point of interest is A, then I calculate my Z over B and my X over B. I come in here, let's say Z over B happens to be 1.1. And X over B, it doesn't matter whether you go left or right, it's the same stress. My X over B happens to be 0.2. 0.1, 2, 3, 4, 0.2. So right about there. My Z over B is 1.1. My X over B is 0.2. That gives me a point right there. I interpolate between. I imagine that there's another curve right here. In this case, it's almost halfway between 0.2 and 0.3. I might be able to say I'm estimating I is equal to 0.25. I is equal to 0.25, estimating between the influence curves. Now, delta sigma equals I times Q. Okay, so you have to visually interpolate between the curves. Now on the next slide, the same thing goes if you're talking about a square load. It's the exact same idea. Not the same influence. You look, it's not the same curves. It's not the same curves. Different influence factors. It's the same idea, similar kind of shape, but not the same numbers. So for a square load, you get a different influence factor than if it was a circular load. And of course, you should expect that. But you use this chart exactly the same way. Now remember, the square is a rectangle. It's a special kind of rectangle where both sides are the same, which makes it a little bit simpler because we don't have a B and an L. We only have a B. It's only one variable instead of two variables. A rectangle has a B and an L, the width and the length of the applied load, whereas a square only has B, which equals L. Okay? So again, we have this square load that is applied at some point. We consider the distance relative to the width of the load, the vertical depth and the lateral distance relative to the width of the load. We get our X and our Z for point A, and we have our Q. We use that to find our point in the chart. It might be like right here, and we interpolate. Perhaps in this case, I equals, well, that's really close to 0.4, not quite as close to 0.5. Maybe I say that is 0.42. Pretty close, 0.42. And then I can say delta sigma equals IQ. Okay? So that's circular load, square load, strip load, or semi-infinite load. That means it's really long in one direction and just narrow width B in the other direction. Same exact idea. Of course, if we look at the numbers here, we look at the numbers and the shape, same idea, use it the exact same way, Z over B and X over B, but these numbers are quite a lot larger than a square. Because a square is a relatively limited area, but a strip load goes on for a much longer area. So larger stresses from the strip load even compared to a square of the same width, right? A square that's, say, 8 foot by 8 foot, compared to a strip load that is 8 feet wide but 200 feet long. The strip load is going to have a much higher stress, but it's the exact same process, okay? But still, we're considering only one variable. What is the width of the load? So the circle, the square, and the strip, you only have to consider what is the width or the diameter of the load, right? But a rectangle has two, and therefore it's a little bit more complicated. So I'm going to ask you to do these ones, and you just read them from these charts in this way. In your homework, get a little comfortable with the circle, the square, and the strip, but they're really pretty easy. So what I'm going to focus on, and what I'm definitely going to ask you about on the exam, is rectangular loads. They're sort of a little bit more complicated because they have that extra variable, not just B, the width of the load, but also L, the length of the load. Okay, so still, in any case, this is true. The only difference is the influence factor. How do we determine the influence factor? The circle, the square, the strip, and the rectangle is the same equation right here, but how do we determine the influence factor? Okay, for the rectangular load, we start with a point load and integrate it the same way as we did all the others, but the integral is a little bit more complicated because, like I've said a few times, it has two variables instead of just one. Okay, so like we would typically do with an integral, sort of starting with, axes like this, and we want to consider the area under the curve, we start right at the origin of the axes and we integrate with respect to x. We might also, in a 2D situation, integrate with respect to y. Well, that's exactly what we're doing here. And because of that, we start at the corner. This is the way the integrals were developed. We start at the corner of the point load. The rectangular load. The corner of the rectangularly loaded area. We integrate it with respect to x. We integrate it with respect to y, as x goes from 0 to the length, and y goes from 0 to the width, b, right? And we're talking about a point below the corner. So you got to remember this, because this is how all the equations were developed. It has to be on the corner of the rectangle. The point of interest down here has to be below the corner of the rectangular area load. Okay. So what does that end up looking like? That integral results in this. A huge mess. I'm not going to ask you to do the integral. We're just going to take the results of this. This is the Boussinesq equation for a rectangularly loaded area. A uniform rectangle load. Again, integrating with respect to both x and y, it becomes a little bit of a mess. We took that point load, integrated with x and y. The result, actually, Newmark then, and hold on a second, that influence then you can recognize as a factor of, well, the depth, but also the length and the width of the rectangle. In those other cases, it was only two variables. In this case, we have three variables. So Newmark, he introduced this concept to further develop the Boussinesq equation. What this is now is the relative width and normalized or relative to the depth. So the relative width, m, and the relative length, n. Now, if it's a square, b equals L. You can still use this technique. I wouldn't say where, if you're working on a problem, it has multiple loads, well, change from the Newmark chart and go to the square just because b equals L. You don't have to do that. The square can be done exactly the same way as we're doing right here, okay? So first of all, the width is always less than or equal to the length. So we got to keep it straight which one is m and which one is n. M is the width over the depth, and n is the length over the depth. This is the normalized or sort of relative width and length of the rectangular area load. Now we have a function of only two things. We have a function of m and n. not B, L, and Z, but a function of M and N. Okay? So again, this relative width, how wide is a wide lode, depends on how deep is the point of interest. Okay, so Newmark, again, introduced this idea. Charts of the solution were developed. This chart is provided on Canvas. There is one in your textbook, but the one that was provided on Canvas is updated. It's newer, it's better, and it's more widely used. Okay, so the one on Canvas, you can actually put it on screen, you can enlarge it, you can make it really big, as opposed to just reading this tiny one out of the book. Also, there are some slight differences. Like I said, the one that I've provided to you looks just a tiny bit different than the one in the book. Okay, the one that I've provided to you has M on the x-axis and N is on all of these contour lines. In the book, it's opposite. So you have to use the one that I've given. Don't use the one that's in the textbook. They're similar enough, but not exactly the same. Okay, so you see on this chart, the legend or the key is given in the upper corner, remembering that the point of interest is always below the corner. This only works if it is beneath the corner. For uniform rectangle loads, this only works if it's beneath the corner. We take M as B over Z and N as L over Z, and then we use those to get I, and then we can say that the induced stress is I times Q. So you need to know for any given rectangular area what is B, L, Z, and Q. For any rectangular area, what is B, L, Z, and Q? And if we know those, we can use the chart to get I, and then once we know I, we can use that to get the induced stress. Okay, so how exactly do we read this chart, right? On the vertical axis, we see the influence values. That's what you're looking for. And you notice that 2 decimal places are given. Your job is to read the chart accurately enough to get that 3rd decimal place. Close enough. We may get slightly different answers based on our estimation from this chart, but we have to get that 3rd digit close enough. All right, so everybody, please focus. It's not really easy to figure out how to read this chart, but that's what we're going to focus on for a minute. So, for any given rectangle, we need to know B, L, Z, and Q. Okay, so M equals B over Z, N equals L over Z. That's the first step. Well, actually, the first step is figuring out, we'll come back to this later, which rectangles to use, and it must be, once again, on the corner. The point of interest, the one point where you're trying to determine the stress, must be below the corner of the rectangle. Okay? Then you have to know B, L, Z, and Q. Get M and N. So let's say that M equals 1. Let's say it turns out that M happens to be 1. You're talking about a rectangle that is, let's say, 10 meters wide, and you're talking about a point that is 10 meters deep. So B equals 10 and Z equals 10. So let's just say that M happens to equal 1. But let's say it is, I don't know, 15 meters long. So the load is 10 meters by 15 meters. And we're talking about a point 10 meters down. So N is L over Z, that will be 1.5. So M is 1, so I come up this grid line right here, and I find where is the curve that matches 1.5? Well, I got a 1.4 and a 1.6. So remember, there's lots of curves. They didn't show all of the curves for the N value. You have to understand that there's another curve that's in between 1.4 and 1.6 that comes down right in between them like that. And so where does this M equals 1 meet with the n equals 1.5. And I'm going to say it's right about there. So what's the value of I? Everybody look at this and you get your own number. I'm going to get my number. What is the value of I for this situation? If m equals 1 and n equals 1.5, what is I?
0.223. Is that what I'm looking at?
No. 0.22 is right here. We are
okay.
We are between 0.1.
Okay, so I'm just following that curve all the way down, not to the actual. Okay.
No, we have a
So
point.
it's 1.86, about 1.87.
Yeah, that's pretty good. I would go with that. 1 point. It's pretty close to the. Sorry,
Yeah, I
not
followed the line all the way to the end of the graph, which is not what you're supposed to do. So it's one.
No.
Okay.
We have come to a point where m and n intersect, right?
Right.
M equals 1 and n equals 1.5. Between this 1.4 and 1.6, right? And this is the point where they intersect. I don't know if this is helpful. Okay. Right there. Okay. So here's 0.18. Read it carefully. We are really close to 0.19. Nick, I think it's definitely 0.18 something, right? So your estimation is only in the third digit, the third decimal place. And you can see it's clearly greater than 0.185 and definitely less than 0.19. So when I ask you to do this, that's the sort of accuracy I require. It's 0.186, 187, 188, right? And I think I'm going to go with 0.187, but you might say 0.188. And so it's pretty easy to be that accurate. Does everybody agree? Is everybody pretty clear on how you use this chart? It's very common to make a mistake like Nick did, following the curves down. No, we're looking for what is the intersection of M and N. And that intersection defines I, the influence factor from the rectangular load. Okay, so for this particular case, I would say I equals 0.187. Then I can take that and put that in right here. Induced stress equals I times Q, now that I know I. All right? Let's do another one. Let's do another situation. One more. Okay? Let's say that this time it turns out that M equals 1.5. Right? Remember, N is always bigger than M. You know what? Not 1.5. Let's go with, well, look carefully. It's a log scale for M on the horizontal, on the x-axis. It's a log scale. Also notice something that I told you in module 3, when we were doing gradation plots, reading the log scale. A log cycle is log base 10 cycle is a factor of 10. So from 0.1 to 1 is 1 log cycle. Notice 0.3 is about halfway in the middle. Same thing as from 1 to 10 is a log cycle, and 3 is about halfway in the middle. Notice the 2 and the 5 the 2 and the 5 are on approximately the third points. So 2 and 5 are 1/3, 3 is 1/2. It's a log scale, so it's 5 is not in the middle, 3 is in the middle. Okay? And you can see how these grid lines sort of get bunched up as they get closer to the end of the cycle. So we all should be pretty familiar with reading log cycles. So if I said m equals 1.5, that's not right in the middle. That's about 2/3. Okay, m equals 1.5 is about 2/3 from 1 to 2. Okay, so use that to help you estimate, right? So what if m equals 1.5 and n equals 3? All right, so I come up here and m equals 1.5 is about 2/3. Here's 1.0, here's 2. M equals 1.5 is about 2/3. M equals 1.5 is that vertical line. Where's n equals 3? Well, there is no n equals 3. There's a 2 and a 4. So again, I have to think about interpolation visually. The n equals 3 curve is actually in between these two. Something like that. So where do my m and n intersect? Right about there. I think that's as accurate as I can be. And right here I see 0.22. And here I see 0.23. So it's really close to 0.23. I might say I equals 0.22 something, right? Just like before. That looks like a 227 or a 228, maybe. Does everybody see that?
Yeah.
Does everybody see how you got the same number as me? Okay. So
You were saying that m is always greater than n, or n is always greater than m?
N is always bigger, right? Because L is always bigger than B. I mean, they could be equal. You can have m
Right.
equals 1.5 and n equals 1.5.
Okay.
But n is always bigger. And so, I just want to point out, depending, you never know what numbers you might end up with in a given situation, right? These curves get a little tricky down here. You have to carefully follow, right? Down like this. Some of the curves actually disappear as they merged with each other, right? So you have to carefully follow down where m and n intersect, okay? And at that point, it tells you I. Okay? So first, understand the idea and be ready to read the chart properly. So if you're off by, if you would have said that that was 0.23 something or 0.18 something, no, it is definitely between 0.22 and 0.22 and 0.23, right? So being off in that third digit is probably okay, but being off in the first two decimal places is not okay. That means you've read the chart incorrectly, okay? All right, so that's the Newmark chart. This gives a graphical solution to that integral for the rectangle. Now, in the homework and in the book, a couple of times I'm going to ask you to solve the problem using the Boussinesq equations. All right, so there are equations for rectangles, and what you might recognize, there's an inflection of the curve. Every one of these curves has an inflection, and there's sort of two different equations depending on the relationship of B, L, and Z. And so you have to do a quick little calc to figure out, should I use the first equation or the second equation, right? So you can use the equations when the problem asks you. But if the question asks you to use the Newmark chart, then you got to come and use this chart. Now, if you're doing this in a spreadsheet, you might want to, try to automate it, or in like a MATLAB program, you can create a MATLAB program that will solve the equations for you, right? But if you're doing, a hand calc for just a couple of points, you don't really want to set up a whole spreadsheet or set up a whole MATLAB program. Well, then you should probably use the chart. I'm going to ask you to be comfortable with both. Okay, so please read the question carefully. If it says use the equation, then you do that. If it says use the Newmark chart, then you have to do that and use this chart. Okay, this is the Newmark chart, which is the solution to Boussinesq's integral. All right, but then that brings us to an important point. What I said was you can only do the corner. You can only do the corner of the load. And on the next slide, it points out that influence factor, I, asymptotes to 0.25. It maxes out at 0.25. So when M is very large, like around 10 or more, and when N is very large, it doesn't take a whole lot, but like it says, greater than 4. When M and N are large, the influence factor maxes out at 0.25. That's the largest possible influence factor. And it's not 0.249 or approximately 0.25. It actually is 0.2500000. It is exactly 1/4. That is the maximum possible influence factor for a rectangular load, and we are always considering the corner of a rectangular load. Always considering the corner of a rectangular load. And so what is the significance of that value? And I shouldn't even write 0.25. Like I said a minute ago, I should probably put it in as 1/4, because that's a lot more accurate. There is no round off that can be considered. Okay? It is exactly 1/4. But when M and N are large, we get maximum I of 1/4. Exactly why is that? What's the significance of that 1/4?